Hey, what's up, guys? This is Sheng here. So this time, let's take a look at today's daily challenge problem, number 823, binary trees with factors. So you're given like an array of unique integers, right? And where each integer is strictly greater than 1. And we need to make, you can make a binary tree using these numbers, these integers, and each number can be used for any number of times. And the requirement is that each leaf node, each non-leaf node value should be equal to the product of the values of its children, right? And we need to return the number of binary trees we can make. And then since the answers will be too large, we need to do a modular by this one, right? And here's the example. So if we have two numbers, we have 2 and 4, right? So for this one, we can make basically 3 trees. So, I mean, the first observation is that, the number itself can always make a tree, right? Because 2 by itself is a tree. Because 2 as itself, it's like, you can think it as a both non-leaf node and a leaf node, right? That's why, the node itself is always, the number itself can always satisfy this condition. And this is 1, and this is another one, which is 4. And the third one is this one, 2, 4, 4. Basically, we have 4, we have 2, then we have 2. Right? Since any integer can be used as many times as possible, that's why with 4 we can make 2 and 2. Okay. And here, so if we have 2, 4, 5, 10, right? I mean, so for obviously we have 4 trees at the beginning, right? And then we'll have like 2, 4, 4, 10, 2, 5, and 10, 5, 2. Right? Cool. So this one, okay, so here are the constraints, right? So we have like the array length is like 1000 and the number range is 10 to the power of 9. Okay. So this problem, it's to me, I was like, how can I was basically I was trying to write a few examples, with some numbers. But so because here in the examples, it only gives you some like very simple examples, right? So let's say if we have 10 and 10, right? So we have 10, 2, and 5, right? But if we have more numbers, let's say if we have more numbers above 10, right? So here we could have built like another numbers here, right? So it's going to be maybe 20 somewhere here, right? And on the other side we have 2 somewhere here. Basically, we can build the numbers, build the trees in this way. And another observation is that since we need to observe make the non-leaf nodes, right, should be equal to the product of the values. So which means that when we build the tree, right, so basically if we think this tree in the bottom up way, right, so basically the number is increasing, which means that the parent node will always be greater than its child node. That's because that's the only only then we can satisfy this condition here, right? And another observation is that whenever we choose like if we have a number, a node 10 here, right? Basically any factors, right, can be its child, right? Oh, let's say 20, right? Let's say 20 is the numbers. Basically, we could have like what? We could have like a 2 times 10 equals 20, right? We also have like what? 4 times 5, right, equals 20. Right? So which means that any of those numbers, as long as they exist in the array here, they can be the child, right, of 20, right? And since we can use those number any number of times, so which means that so it's better for us to sort this array first, right? And so now we have like a dynamic programming concept here. basically, let's say if we sort the array from smallest to the biggest, right? And then whenever we have a I here, we have a DPI here, right? So which means this DPI means that the total number of trees, right, we can build by using I as a root node. So in this case 20, right? So which means that we're gonna loop through. Sorry, this I is like the ice number, right? So basically, which means that we're gonna loop through from dpj, right? Times dpk here, right? So this is gonna be a plus equal here. Okay, so which means that let's say if we have 20 here, we can loop through the previously numbers because that's the only possible way we can find the child node for this current one, right? So first we have the j here, right? And then we need to use the j to find the other numbers 10. Let's say we are at 2 here, right? And then we need to know, okay, do we have a 10 in this array? I mean, if we do, then okay, obviously the total combinations or the total different ways to form a binary tree with these two numbers is a DPI times DPK, right? Because let's say for this J's number, if we have like 4 different ways to form a subtree, right, by using this J's number as a root, and then if we have like 3 ways of forming the subtree with this case number as a root, then the total combination for the current like what the ice number will be 4 times 3. It's going to be 12, right? So now I think the DP transition function is kind of clear. Basically, with each DPI here, we loop through the numbers from 0 to j, right? Where the j is smaller than I. Okay, and then with each j index here, and we know the number of the j index, and then we can calculate the other numbers, the other number of the tree of the child here, right? So and if the other number doesn't exist, right? So if the other number doesn't exist, which means that the child is the same as 20, right? Sorry. So okay, what I mean that, so if the other number doesn't exist, of course, it's the we won't need to accumulate that number. And if there's a special case, let's say if there's a 20, another 20 after 20, let's say we have 220 here, right? So 20 can also be a 20 like this, right? So this is also a valid tree. Okay, but this one actually this is a special case, and we can simply ignore this one because this one will not increase any of the ways we can build the tree, because this one is the same, because we cannot have another like node on the other side, because each number is strictly greater than 1, right? So the only possible way we can have is the 1 here, but there's no node 1 here. That's why for this one we can simply ignore it, because it's a special case that we won't consider in this case. Cool. So I think that's pretty much it is, right? Basically, since we stored the array first, and and we process from the smallest number to the biggest number, right? And whenever we're at I here, so basically both the number of j and the number of k will be the dp I and j and k will be smaller. Had already been processed before. So that's how this basically the DP works, right? And yeah, I think let me try to start coding. So like I said, first we want to sort. and we have an n length of array, right? And then we need to define a DP here. So I started this one with 1 because the reason being is because the number itself can also form a binary tree. That's why for each of the numbers, the count will be 1. The initial count will be 1. and another one is that we have to somehow let me see. I think I will create like a set here, so that we can easily check if the other number exists in this array or not. That's why I'm doing this kind of set array, right? And then for I in range of 1 to n, right? We do a for j in range I, right? Basically, if the array I, right? So if that's the I number can be divided by is divisible by this array of j, right? Then I get this number 2, right? So assuming we have this number 2 here, then we have array I to a modular by array j, right? And then I check if this number 2 in this array, right? In this array set. Then I do dp I plus dpj, right? Times a dp of this number 2. We need to find the index of that, right? Because we use index to represent the dp here. So which means we can do this one. I mean the nums index, right? We can always not num. So this array dot index of num2, right? And then we can just use this one index 2. Yeah. So this is one way of doing it. And then okay, let me finish that. Maybe we can improve that a little bit later on. So and then next we just simply do the output, right? So first let's define this mod here, right? +7. And then we just need to return the sum, right? The sum of dp to a modular of mod, right? So I think this should work. Okay. Yeah. So this one works, right? I mean, but the time complexity for this one, I think we have four loops here, so it's gonna be n square. I believe this one, this index in the array, this is also like a O of n, right? But I mean, we can improve this one a little bit, so which means we can build like a num index a dictionary for at the beginning, right? So where the key is a number and the index will be I, right? For I dot number in enumerate array, right? And here we can simply use the number to find the index. Yeah, I think that's that's just the way we should do it, right? Yeah, this one should also work. Cool. So now the time complexity for this one, obviously, is O of n squared, right? And the space is O of n, right? Yeah, cool. I think that's the way, right? That's the logic to solve this problem. It's like, so the idea behind this one is like the things we can. So first one is we have to sort this array because that's the only way we can use apply the DP idea to this problem. So which means that every time we have a number here, the DP ith number, if we can find like a child, right? Both left child and right child exist in the in this array here, basically we'll do a dp I times dp the other one, right? And this 5 2 and 2 5 has already been handled by this one because when we loop through the j here, if we'll basically the j will be both 2 and 5, right? So which means we are counting for all the scenarios here, and right, and the key idea here is that we have to we have to be able to realize that so every time after calculating a value for the current ith number, like let's say for example 20, those stored number stored number can be used, for the further calculation. That's why basically that's how this DP idea comes from, right? Yeah, as long as you can figure out this one is a DP problem, and the rest will be just do a sort and then do some like a regular like DP traverse, right? Basically for each of the number here, we try all the previously possible child candidates, right? If we can find a match, right? If we can find a match pair of the child, we do this apply this multiply, right? And we accumulate it to the current DPI here. In the end, we do this sum DP, right? Because since basically we're accumulating all the possible numbers, right? Basically this one is sum DP means that we accumulate all the possible binary trees, for any number, right? For all the possible numbers as the root, and we do divide it by mod. Cool. I think that's everything I want to talk about for this problem. Yeah, and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.